In this session, we're going to talk about errors and uncertainties. So these are the objections for today. We're going to introduce what errors and uncertainties are. Then we're going to talk about systematic errors, random errors, and accuracy and precision. Then at the end of the session, we're also going to talk about uncertainties in details. We're going to solve some questions. So what are you supposed to understand? When you're measuring a quantity, there's usually what we call the measured value, and the true value. Okay, so errors and uncertainties in measurements, they will refer to the difference between the measured value and the true value. So that's where the difference is, what you've measured and what the true value is. So based on that, there are going to be variations, and based on those variations, that's what we're talking about now today, talking about what will be now the difference, or what kind of errors can you make as you're comparing the true value and the measured value. So there are two types of errors that you're supposed to understand. Broadly, there's we've got what we call systematic errors or systematic errors. Then secondly, we've got what we call random errors. So these are the two types of errors that you are supposed to understand as far as physics is concerned. Now, what are systematic errors? Systematic errors, these ones are predictable errors. They are predictable errors. Number two, they are consistent errors. Three, they are repeatable errors. So lastly, these ones, they occur in the same direction. Now, these are powerful concepts to understand if you want to decipher what systematic errors are. So number one, they are predictable. You're able to predict in which direction they are going to go. Number two, they are consistent. You are always getting, they are consistent and repeatable, meaning you'll be getting one figure over and over and over again. An example that you can give is, maybe you have a scale that is always reading 3 grams over the actual weight, okay, probably due to some faults here and there. So what you are supposed to understand is that where do these errors usually come from? What are some of the sources? What are some of the sources of systematic errors? So someone can make an error, a systematic error, due to maybe a flaw in some flaws in a measurement system itself. Sometimes even just calibration errors. Sometimes even just the environmental influences, okay? Sometimes the procedure that you are using, procedural errors, okay, can lead to you having a systematic error. Okay, what are we talking about in these flaws? We're talking about flaws in an instrument. An instrument, sometimes, let me say you're using a microscope, but your microscope is scratched, the lens is scratched, meaning you're going to be getting distorted images consistently, and that will lead to a systematic error. Then calibrations, probably you have miscalibrations. Okay, miscalibrations. So a scale that has not been, for example, for maybe, let me say you have a scale that has not been set to 0 before you are using it. Okay, so let's say your scale is already, before you even put anything, it's 0.2. So because of the scale itself, or you've calibrated it wrongly, that will cause these systematic errors. And because of that 0.2 that you are going to have a certain figure over and over again. Then we're talking about procedural, the method that you are using. Probably the method that you are using, the experimental method that you are using might be wrong. Therefore, you're going to be getting a very predictable or a very repeatable answer. Okay. Then sometimes the environment itself, probably the conditions in the environment change, that might affect also, your experiment or your values. Then sometimes also maybe we can also talk about maybe biasness. Okay, observer's biasness. Maybe due to your beliefs or maybe expectations of this experiment. Maybe you're expecting, this experiment to give me a green, this experiment to give me a green. Probably you might have missed something and it will automatically give you a green because that's what you are expecting from the experiment. Okay, so this is very, very important for us to understand. Now, a specific example that I've just given on systematic error is the one that I've just talked about, the 0. Okay, now the 0, this one is called a 0 error. It's a specific type of a systematic error. Okay, now what a 0 error does is that an instrument does not read 0 when the measured quantity is 0. Okay, so you put something but an instrument never reads 0. Okay, for example, a digital balance, you're measuring mass, but the balance is showing 0.4 grams. Okay, so when nothing is placed on it, it's already 0.4 grams. Now, just this 0.4 grams can lead to overestimation. Overestimation of your values. Okay, therefore you're going to be getting, let me say, errors in your in your measurements. Then, second, we've got what we call random errors. Now, what are random errors? Okay, so they are like the opposites, kind of like of the opposite of what I've just from talking about systematic errors. These ones will be unpredictable. Okay, there'll be unpredictable variations that occur in there is no consistency. No consistent. We're talking about a pattern here. Okay, so what can be the causes of these ones? What can be the causes of random errors? Random errors, probably they can come from, let me say, maybe you're observing from a different point, so observers variations. Okay, this one sees this from this angle, the other one sees it from the other angle. Therefore, you're getting different answers. Sometimes just noise itself, electrical noise. Sometimes also maybe just unpredictable fluctuations. Okay, now these fluctuations are talking about fluctuations in the environmental conditions, maybe like the temperature. We're talking about things like the humidity, the amount of water vapor at that point during the experiment. These things are going to affect your results. So the way these maybe a good example on random errors is maybe you're getting repeated measurements of the same quantity due to maybe a slight change in the experimental setup itself. Now, the previous errors that we talked about, systematic errors, you can just correct them. They are easily corrected. You can easily correct systematic errors, unlike random errors. Because for random errors, how are you going to change the way the observer sees something? How are you going to change the fluctuations in temperature? So it'd be very hard for random errors to be changed. But for systematic, probably if it's the instrument that has a problem, probably you can just fix it or buy a new microscope. But for this one, it will be very hard. So you can rather, it doesn't mean we're not supposed to do anything about it. We can maybe just reduce them. So how can we reduce random errors? We cannot fully eliminate them, but how can we reduce? Because we want to reduce these errors as much as possible. Okay, so mostly what we do to reduce random errors, we increase the sample size. Okay, so when you increase the sample size, it means there are a lot of averages that you are going to get, which is even better. Okay, so you are taking more measurements. Okay, so this can help you to average the random errors, what we are calling as repeated measurements. So what do we mean? So you can measure, let's say you've measured the first instance, the second instance, the third, let's say the fourth. Let's say you have measured your temperature. Your temperature this time, let's say it's 20 degrees Celsius. The next one maybe is 20.1 degrees Celsius. Maybe the other one maybe is 20 point, maybe let's say 1 degrees Celsius. Maybe the last one is maybe, let me say 24. Now 24 in this case would be like an outlier. So because of these variations, you're just going to add all of them and divide it by 4. In case we're just talking about, you're going to find the arithmetic mean, the average, so that you reduce that random error as much as possible. Okay, then because we're talking about errors, there's an aspect of accuracy and precision. Now, what is accuracy itself? Accuracy, we're talking about how close measurements are to the true value. How close are you to the true value? Because we've talked about the measured value and the true value. So you're trying to compare what the true value is and what the measured value is. Let's say the true value of what you're finding, let's say, is 20. Then you've measured, let's say 10. How is 10 close to 20? So that's what we're talking about as accuracy. Okay, so an example, let's say if the true value, let's say, is 20, this is our true value. Then let's say you have measurements like your measurements when you're measuring let's say let me say your length. Let's say you've measured 20.1, you've measured let's say 19.9, let's say you've measured 20.0. Now these measurements are very, very much accurate. Why? Because they are very close to the true value. Okay, so that is very, very important for you to understand. Then there's what is called deep precision. How close the values are to each other is what we call precision. Okay, so to the true value and to the measured value, we're talking about accuracy. But now those same values, how close they are to each other themselves, is what we're calling precisions. For example, you can have measurements, let's say 5.8, maybe you have a measurement 5.7, maybe you have a measurement 5. Let me say another 8. This will show that maybe we can say this will be very precise. Okay, it will be very precise because they are very close to each other, but it might not be accurate if the true value, let's say the true value is 6. If the true value is 6, this might not be accurate. Okay, because the true value is 6. So that's what I'm talking about. So that is very, very, very important for you to understand. Now let's solve some questions. Let's just put this into context. Let me draw 4 diagrams to just explain on something. Let's say this is our circle, or let me say this is our dartboard. This is the first one, this is the second one, this is the third one, and this is the fourth one. Okay, so this is the middle point. Okay, or what we call the bull's eye. This is the bull's eye, the middle point of a dartboard. So we're trying by all means to hit the middle target. So let's call this one as scenario A, scenario B, scenario C, and scenario D. Okay. So let's say in the first scenario, you shoot. You get your dart, you shoot, and you hit this point. The next one, you hit this point. Let's say the third one, you hit this point. Now you have to comment on accuracy and on precision. So this one, it just shows that there is low accuracy. Why? You are very far from the true value. Okay, all your values are very far from the true value. Then what about precision? Are these values very close together or to each other? Overwhelmingly no. So this has low precision, meaning it's not precise. Okay, let's come to scenario B. Now scenario B, let's say in this case maybe you're a bit, I don't know, but you're just throwing. Let's say the first one you hit this point, the second one maybe you hit this point, the third one you hit this point, maybe also try the fourth time you hit maybe this point. So what will be your comment on accuracy and on precision? Okay, so this is low accurate. Okay, there is low accuracy in here. Why? You are very far from the true value. Okay, what about precision? Look at these values, they are very, very close to each other. So there is high precision in this case. Okay, this is about the second scenario. What about the third scenario? Let's say this time around, you are trying to, let's say you are hitting the points very nicely. At least let me use a different color. You've hit this point. Let's say you've hit this point, you've hit this point. You are hitting the middle, yes. So what is this going to be? So you're going to have, you're able to see that this is, you have high accuracy. Okay, why? Because all your points, all your darts have, they were hitting on the true value. Okay, but what about precision? But like in this case, they are a bit, not very close to each other, so it will have low precision. When we come to the last one, let's say now you are just hitting at least the good target, the middle point. Okay, when you are meeting on the middle point, you'll be accurate and you'll be precise. Okay, you are very, very accurate and precise. So this is very important to just put it into context. Okay, now why do we talk about accuracy and precision? It's because these two measurements, they are necessary for comprehensive scientific analysis, because you want to come up with credible experimental results. Okay, so that is very, very important for us to understand. Now sometimes it can be uncertainties in measurements themselves. So what about uncertainties? What about measurements themselves? So when talking about, when we ask you, when you say you are uncertain about something, meaning you are not very, very sure with what you did. Okay, so when I'm talking about uncertainty in measurements, in this context, we are acknowledging that there are limits to your precision and accuracy to what you've gotten. Are you precise? You are saying yes, but how precise are you? Okay, you say maybe I think I would have made some errors. How much errors? Okay, accuracy, are you accurate? Yes, I'm very accurate. How accurate are you? Maybe you say I'm 90% sure, and maybe you say I'm 95% sure. Maybe I'm saying, but if you say you're 100% sure, meaning you're very much certain, right? But uncertainty in measurements means you're not very 100% sure. So because you're not very much percent, what is your margin of error? So if I say 95%, I'm 95% sure that I've gotten, let me say I've gotten an 80%, a 90% in a test. It means I've left 5%, error. This 5% that I've left is what we call the margin of error. So that's the margin that I've left because I'm not very 100% sure. So now there are two types of uncertainties that you're supposed to know. Okay, there's what we call absolute uncertainty and two, relative. Others might call it percentage uncertainty. So what I'm just talking about in terms of percentages, 90% and 95%, that is about percentage uncertainty. Okay, now let's talk about absolute uncertainty, because you can't find percentage percentage uncertainty without finding your absolute uncertainty. So in this case, for the absolute uncertainty, your margin of error is expressed in measurement as a range. Okay, a range in terms of, let's say, positive or minus a certain value. Okay, let's say you've measured, and after measuring maybe, let's say, your length, you found your length to be, let's say, 10 centimeters. Now, what is your margin of error after measuring your measurement? So you can add what we call an absolute uncertainty. Now for an absolute certainty, you can put positive or minus, let's say 0.5. Sometimes you can also say 0.1. Okay, this is what we call the absolute uncertainty, meaning to this number, at least there is a range. Okay, there is a range to let me say 0.5, or let me just say 1. If you have an absolute value of 1, meaning you have left you've left a very large margin for errors. Okay, but the more it's getting smaller and smaller, meaning we are becoming more and more accurate. So if I say my margin of error is 0.5, this might be bigger compared to 0.1, meaning I was as much as accurate as possible. Okay, so let's say you have 0.5. So it means to 10 I'm going to add 0.5, and to 10 I'm going to subtract 0.5, and that will give me a range. When I add, I'm going to have 10.5. When I subtract, I'm going to have 9.5. Okay, so this will be the range. The range will be, if my value will be between 9.5 and 10.5. Between these, that's where my true values are. Okay, I've left a certain margin of error. Okay, that's about absolute uncertainty. You are very sure that it is 0.5. You are very sure that it is 0.1, error that you've made. So that is very, very important for us to understand. Now, on the other hand, the way you find your percentage, uncertainty, you're going to say a percentage, let's say percentage uncertainty will be equals to the absolute uncertainty over the measured value times 100%. So this is how you find your percentage uncertainty. Okay, so let's say you are measuring you've measured 10 grams, or let me say 10 kg. To 10 kg you've put maybe positive or minus 2. Okay, let's say kg. So that is just an example. You know that positive or minus 2, it is an absolute uncertainty. So for you to find your percentage uncertainty, you're going to get a 2, you're going to divide it by 10, you're going to multiply by 100. So this and this will cancel, therefore I'm just going to have a 20%. This is my my percentage uncertainty. Okay, so from 100% minus 20, that will give me 80%. So this means that I'm 80% sure that the answers that I've gotten are correct, but 20% I think I'm I've made a mistake somewhere. So that's about percentage uncertainty. Now these uncertainties we talked about can come, yes, from environmental factors. Probably you are doing an experiment and the temperature just changed, okay, because the temperature will not be constant. Probably there are methodological factors. Probably when you're mixing something you made a mistake, or maybe you've added more or less. Therefore that's why you are trying to add a positive or minus to that quantity in case there's any underestimation or overestimation. Now what if now you're adding let's say 2 or more uncertainties? Or subtracting them? You have got 2 uncertainties. The way you're going to find the total uncertainty, there's a formula that we use. You are going to do the square root of, let's say, the first object that you are measuring, that is A, so you're going to square it, plus the second object that you are finding, that is your B. Okay, so in this case that's what you are using something like the Pythagorean identity, or let me say the Pythagoras theorem. So let's say we have an example. Let's say you have 2 lengths, okay, that you've measured. Let's say A, let's say you found, let's say 30 centimeters, okay. Let's say B, let's say you found maybe 20 centimeters, okay. For A, the margin of error, let's say you've put your absolute error as, let's say, 0.3 centimeters. For B, let's say you've put positive or minus 0.2 centimeters, okay. So this is what you have. Now what will be the total length of this when you add, because you're adding or subtracting, but in this case let's add 30 plus a 20. We know that will give us a 50 centimeters, okay. But now the total uncertainty, we are uncertain for the first one, we are uncertain about 0.3. For the second one we are uncertain about 0.2. So for us to find that total uncertainty, unlike the length, we're going to find the square root of 0.3 squared plus 0.2 squared, okay. And what I get is 0.36 centimeters. So therefore now my total length of these two will just be, it will be 50 centimeters that I found, plus or minus the 0.36 centimeters that I've found. So this is how you add and subtract these uncertainties. So this is a very interesting topic. So we're going to end here today. See you in the next session.